For homework 10.9, we were looking at the different energy levels and how we could actually calculate the light that comes out of them. So, again, Model 1 looks just like Model 1 from homework 10.8. In each case, an electron sitting in an excited state, quote unquote, falls down to a lower energy level. Now, when it falls down, that energy in that electron transition has to turn into light. It has to turn into some other form of energy in order to have energy conservation. So, like I mentioned in the last video, you don't need to know off the top of your head that transition A is reddish in color and transition B is bluish in color or greenish in color. But you should know off the top of your head that these two are within the visible spectrum of light. They're between 400 and 700 nanometers. So for transition A, I'm going to use this information from above. The wavelength is 680 nanometers. And so I can use the 680 nanometers in the second half of this equation to solve for the energy. Now, if you're having trouble with what this equation looks like, let's just leave it as energy A is hc. So hc is Planck's constant times the speed of light. But if I put it in these abnormal units of electron volts times nanometers, then guys, I don't even need to convert this into meters. The nanometers cancel each other out. So let's just use this one, okay? So 1,240 divided by 680 leaves 1.81 electron volts of energy. Electron volt is a very, very, very small unit of energy, but that's okay because I don't want something like red light to have so much energy that it like damages my skin when red things are nearby me. I wouldn't like that, right? So let's take transition B, substitute in its wavelength from the text above, get its energy, still very low energy, and just for orders of magnitude here, a regular chemical reaction lets out thousands of electron volts. A regular nuclear reaction lets out millions of electron volts. And that's why nuclear reactors use so much more energy efficiently than using a chemical reactor. Okay, so in letter C then, the total energy of transition C. Well, if A is 1.8 and B is 2.2, then C, well, those energies need to add up. C's energy must be just add these two together for the 4.06 electron volts. Still, ultraviolet, you're now going to start getting into the range where this is going to start being enough energy to pull electrons off your DNA. If I get a chance, I'll talk about this on Monday when we do photoelectric effect. But if you hit a cell with so much energy coming in, you have enough energy to cause the electron to straight up jump out of your atom. And if that atom is part of a DNA molecule, then you could have an unscheduled mutation to your DNA, which causes cancer and is dangerous. So let's take our wavelength. We get our wavelength by doing the same equation we did with A and the same equation we did with B, but now we're taking the energy, the 406, and substituting it in to find wavelength. If you're wondering where I got the second equation from, I took the first one, multiplied by wavelength on both sides, then divided by energy. So if this one is red and this one is green, then C must have more energy than either red or green. It must be in the ultraviolet area of the spectrum. So the visual or the visible emission spectrum for an atom would only see A and B because C has too much energy, you actually can't see that. So I would draw one line for A, one line for B. And if white light, which is made of all the colors, Roy G. Biv, hits these little gases, those are gases that I drew there. Notice how orange, yellow, green, blue, indigo, and violet, they all pass right through. they all pass right through because when white light hits these gas atoms, it moves electrons up from the ground state. Let's look at the ground state. So that could either be A or C. It actually can't be B. Talk to me about that later if you have a question. But it can't be B because your electrons start in your most stable state, your ground state. And when light hits them, it can either move up in transition A or transition C. So transition A is the only one that falls in this category. So the red light for transition A gets absorbed. This atom that red hit gets excited. That's what the little star is supposed to mean there. It's excited. And all the other colors pass through as if nothing is there. And if that sounds funny to you, keep in mind that most gases are transparent. They might absorb a little tiny bit of light, but most gases are transparent, so that's not new. Model 2. The homework we just did yesterday also had Model 2, and Model 2 worked in the same way. But today I'm having you use Model 2 to practice a calculation here. So, measure the wavelength for the highest energy spectral line for lithium. So I'm going to go over to lithium, and the highest energy spectral line is actually going to be the smallest wavelength, so is this one right here. And I called that like 460 nanometers. If you called it something slightly different, your answer will be slightly different than mine. No big deal. So I took my wavelength, used the wave equation to find frequency, took my energy equation, used the wavelength to find energy. Just like yesterday, in order to figure out what materials are in this mixture, I'm going to match up the lines. And in this case, I see strontium has 1, 2, 3, 4, 5, 6, 7, 8. All of its spectral lines show up in the mixture, so strontium's in there. But it can't be cadmium because see this pair of lights right here? Those energy levels don't show up in the mixture, so it can't be cadmium. But if I pair up lithium, lithium's 1, 2, 3, 4 spectral lines are in the mixture, so lithium must be in there. So let's say I look at a star, and I know a star has this correct mixture here. And if the star is stationary, it looks like this, where those lines represent the different energy levels allowed by this particular atom. Okay. Now, an astronomer, that's the word I was looking for, looks at that spectrum and sees that all the lines are slightly shifted red. Right? So this line got shifted towards red, this line got shifted, this pair got shifted. Gets moved towards red. That means the star is moving away from you. And I tried to put a picture here in the model I sent out to you guys. If the car is moving away from this observer sees long wavelength, low frequency. And my long wavelength of light is red. Red light or red shifted starlight means that whatever you're looking at is moving away from the Earth. The Earth is at position Y. If we look through our telescope and we see that all the light is blue shifted, same line, but shifted towards the blue higher energy end of the spectrum, that means the waves are getting compressed close together. That galaxy or star or whatever we're observing must be moving towards us. So the Doppler effect means long wavelength is moving away, red has long wavelength, ergo red shifts means the star or galaxy that you're observing is moving away. Now, a disturbing thing about the universe is if we look out at the universe, every single galaxy in the universe that's not in our very close vicinity. So we do have like a small satellite galaxy, the Andromeda galaxy that's near ours that doesn't do this, but literally every other one is red shifted. That means every single one of those galaxies is moving away from ours. If all the galaxies are doing this, that must mean all the galaxies are moving away from each other, and ergo, the universe is expanding. The reason I say it's kind of frightening is because that means over time, we'd eventually get so far apart, our galaxy and all the other galaxies, that eventually the stars would begin to go out. those galaxies would get so far away that their light could never reach us, ever. And that leads to some other problems on how do you sustain life when your stars grow and have life cycles. So I had you watch this video about star formation, and we talked about how, in the video they talked about how at the beginning of the life of a star, every single star burns hydrogen into helium. The hydrogen exists at the beginning of the universe. It gravitationally attracts other atoms over time. And when there's a large enough agglomeration because of that gravitational attraction, this gas gets so hot that fusion begins occurring. And hydrogen has 1 proton. Hydrogen starts fusing into helium, which has 2 protons. Starts fusing into lithium, which has 3 protons. And so on. So hydrogen, helium, and a little tiny bit of lithium are in every star. And that's why they've got these X's all the way down in their charts. The youngest stars would only have hydrogen and helium and a little bit of lithium. The younger your star is, the fewer elements it's had time to process. Now, older stars then are going to be stars that have been burning and fusing higher and higher proton level elements over time. So star number 2 has to be my oldest star because it has all of the elements in there. It's had lots of time to process. Okay. If you were stuck, and I got a few questions on 4D. If you were stuck on 4D, it's really from the video. So what you needed to do here was watch this part of the video. So in this video, the main sequence stars, like our sun, is right here. It's about halfway through its 10 billion year life cycle. The star starts really bright, really hot, and blue. The more energy it has, the closer to the blue end of the spectrum it will be, because blue and violet has more energy than red, right? So our star would start as very hot, very bright, and blue in color. And over time, stars will get larger. I'm actually going to take the giant path here. They'll get larger, but they do actually get cooler. Sad thing is, in the life of our star, our sun, we suspect that our sun will turn into a red giant along this path. If it does that in the way that's predicted, the star will gain in radius, it will lose temperature, but when the star gains in radius, the sun has a distinct possibility of its radius going past Earth and Mars. Its radius would be right around where the asteroid belt is now. So think about all the freestanding structures we have on Earth being absorbed by the sun. Bad news bears, but we won't be there for it, so it's fine. So for main sequence stars, red giant, larger in radius, cooler than temperature, the sun would absorb the Earth, possibly Mars. Not great news for us. Okay? So finally, based on the evidence of the composition of stars, the most common elements in the universe were hydrogen, because hydrogen was formed in the Big Bang. It's 1 proton, so it's not that difficult to form, right? Hydrogen fused into helium, fused into lithium, so those 3 are the most common. They come from nuclear fusion that occurs in all stars. All stars start by burning hydrogen into helium, then helium and hydrogen into lithium, and so on and so forth throughout the periodic table of the elements. And for most stars, they're burning hydrogen into helium for the majority of their life. Most stars don't spend a lot of time making the higher elements, and actually some new physics shows that those higher elements may not actually come from where we think they do. So, thanks for watching. Best of luck to you all. Email with questions.